Thank you very much, and I would also like to thank the organizers for having me. It's a great pleasure. So this talk will be about the Navier-Stokes equations, which I'm sure everybody knows. Incompressible, and I will set the viscosity to 1. And let's say the equations are posed on a 3-dimensional torus, but this is irrelevant for anything. So also it's convenient if we work on the torus to fix the mean to be 0. So throughout the talk, the mean of the functions are 0. So this equation is of course well known, and the notion of solution, there are many, many notions of solutions you can work with. And the weakest possible notion of solution is that of a distributional solution. So you basically multiply this formally against the test function, throw all the derivatives on the test function, and that you call the weakest possible notion of solution. So for that, you notice that you can write this in divergence form. So this is the divergence of V tensor V. And that allows you to throw everything onto the test function. So a continuous in time weak solution, that's the notion of solution I will work with, is a vector field V, which is C0 in time, L2 in space. It's weakly divergence free for any time. And moreover, it obeys the Navier-Stokes equations in the sense of distributions. So you have this 0 is equal to the integral over the torus of the initial data phi of xt, x0, sorry, dx plus integral 0 to t, integral over the torus, and then it's v dotted with dt phi minus Laplacian phi plus v dot grad phi dx dt for all phi which are C0 infinity and divergence free. Okay. So notice I've slapped all the derivatives on the test function, so this makes sense as soon as V is L2. Because the only non-trivial thing here is that this product makes sense. And if V is L2, this makes sense as an L1 function. Okay, this notion of solutions was first considered by Serin in '63, because it's the weakest one, as I said. Now, I should say that weak is mild. This is, of course, the celebrated result of Fabes, Jones, and Riviere, which says that this notion of weak solution is exactly the same as this notion of weak solution. Which is so-called the mild formulation, and these two are the same concept in this regularity class. Here, the bold P is the Leray projector, as usual. Okay. So notice these are not Leray solutions. Leray proved in '34 that given any L2 initial data, you can construct a weak solution to the Navier-Stokes equation, but it's not exactly this notion. So his result in '34 states that for any V naught in L2, there exists a global in time weak solution. Well, I guess it's weakly continuous. But it's also square integrable in time with values in H1 dot. And moreover, and this is the key aspect, they obey the energy inequality. So V at time t, L2 squared plus 2 times integral s to t gradient V of tau, L2 squared d tau is less or equal V of s, L2 squared, for almost every s positive, and then for all t larger than s. So notice we are missing this, the energy inequality, and we are missing this. On the other hand, our solutions are strongly continuous in time. In fact, they're Hurler continuous in time. So these notions are not exactly the same notions of solutions. All right. About Leray solutions, you can prove, however, very nice things. For those solutions, you cannot even prove existence in principle, because to prove existence, you would need to prove that there exists a fixed point to this mapping, and for that you need to be in a scaling invariant space, or better. Otherwise, you cannot prove a fixed point. So about weak solutions, much is known, and I will not attempt to give you a whole history about that. So let me just mention partial regularity in time. If you'd have any H1 initial data for Navier-Stokes, then for time, which is proportional to the H1 norm to the power -4, you have a local in time unique smooth solution, and its size doubles at most. And because you also know that for Leray solutions, the H1 norm is square integrable, you can somehow measure the number of time intervals where the H1 norm can be big. And then given this information about the local time scaling like H1 to the -4, you can deduce partial regularity in time, and this was done by Leray. But of course it was formalized in this, in the word that we're using now by Scheffer in 77. And the theorem goes like this: if there are singularities in Leray solutions, then you would call sigma sub t the singular time between 0 and t, and the Hausdorff dimension of the singular set of times is less or equal than 1/2. So Hausdorff dimension of the set of singular times is less or equal to 1/2. Of course, it could be empty, but that's the best you can prove. Now, of course, you can prove partial regularity in space and time by doing yet another notion of solutions, which are called suitable weak solutions, in which you basically require this inequality not just to hold integrated over space, but locally in space as well. And then, of course, there are the cerebrated results of Scheffer, again, which, who proved that the parabolic Hausdorff measure of the set of singular spacetimes is Hausdorff mentioned 1, and then Kafelik and Nierenberg, who proved that the 1 Hausdorff measure is 0. And there are other more interesting proofs of this result, or not more interesting, different proofs of this result by many people, Fangualin, Alexis, Vasseur, Kukavica, and other people. Of course, uniqueness of Leray solutions is today open, and since we don't have uniqueness or regularity, we do have, however, conditional uniqueness and regularity results. Let me say. And these come in several flavors. The most classical flavor is the one where scaling matters. You basically ask yourself what norms are invariant, are there natural scaling of the Navier-Stokes equations, which says that if u is solution, then u of xt, which is lambda u of lambda x lambda squared t, is also a solution. And then because to leading order, this is a semilinear parabolic equation, if you assume a priori information on a scaling invariant norm, you have a hope of proving regularity. And this kind of theorems goes under the umbrella of Prodi-Serin criteria. First examples were proven by Ladizhenskaya and Kiselev and Ladizhenskaya, then by Foyash and Prodi, and then Prodi and Serin. So I guess today they carry the Prodi-Serin criteria. criteria, and they go as this. So of course you need to choose a scale of Banach spaces to measure invariance. So the scale of Banach spaces considered typically is LP in time, LQ in space. And then you have 2 time dimensions. You have 3 space dimensions. And if this is less or equal 1, you have regularity. And of course, if you're equal to 1, that's a scaling invariant space. There are theorems. There are theorems even for the endpoint, p is equal to infinity, except that is much harder. So the p is equal to infinity case was established in 2003 only by Escariaza, Seregin, and Schwerak, and that requires a completely different set of proofs. Because the L infinity norm, when you shrink a parabolic cylinder, does not shrink. There are other conditional regularity results which are not of this type. And I am aware of only 2. The first one deals with the direction of vorticity around the possible singularity. And so this is the line of work initiated by Constantin and Pfefferman. And there's other kinds of results which assume a sign, and it's convenient to assume a lower bound on the pressure. And this is a result of Seregin and Schwerak. Okay, so the first one says that if the vorticity direction has certain regularity around a singular, around a putative singularity, then in fact there is no singularity. And the second one says that if you have a lower bound on the pressure, the solution is smooth. A suitable weak solution is smooth. So these conditions, there's a conjecture that they're sharp, the scaling conditions. So this is one of the important open problems is, are the Prodi serine conditions sharp? And I should say one thing. If you're trying to prove Prodi-serine criteria for mild solutions, they are exactly the same except for the endpoint. As far as I am aware, the endpoint, the L infinity N3 endpoint is open for mild solutions. Instead, you can do C0 L3. And that's an old result of Lyons and Masmoudi. And just to emphasize, mild solutions, they don't know what the energy inequality is, right? They have no idea. Okay, so there is a conjecture by Gia and Schwerak who say that as soon as you depart scaling by a little bit, namely instead of L infinity L3 to consider L infinity weak L3, you could already break uniqueness. So uniqueness may already fail in L infinity in time, weak L3 in space. And they have this conjecture, basically is a conditional theorem. If the spectrum of a certain linearized operator, which has a free parameter, which is in some sense the size of the object you linearize about, if this spectrum crosses into the unstable part of the complex plane as this parameter increases, then you have non-uniqueness of Leray solutions. And there are numerical works by Julien Guillaume and Schwerak who have done numerics, and this spectral crossing appears to be present, at least in the numerical work. So from this point of view, this conjecture looks very convincing, but of course a proof is today open. Okay, so what I will talk about today is to tackle the non-uniqueness problem for weak or mild solutions, however you want to call them. But instead of attacking the problem by going just below scaling, which is what this conjecture does, we will go just from the opposite end. So let's take the worst possible notion of solution and try to first prove that they are not unique. And I guess I should state a theorem. And everything I'm saying today is a joint work with Tristan Buckmaster and Maria Colombo. And the theorem can be stated in many ways, so let me state it in the way that's in the paper. There exists a parameter beta larger than 0. Think of it as 10 to the minus 10 if you want, such that the following holds. Given any time interval and given any two strong solutions, smooth solutions of Navier-Stokes on 0t. So given 0t and any two strong, i.e. smooth, solutions of Navier-Stokes on 0t. They don't have to have the same initial data, right? Otherwise, this would be a very silly statement. Let's call them U1 and U2. So, strong solution, I don't know, C0H1 or better, whatever is C0L3 is good enough. So given such things, there exists a continuous in time weak solution. Exists U, a continuous in time weak solution. With regularity U is C0H beta in space, so it has a tiny bit of a derivative in space. And the associated vorticity is C0 in time L1 plus beta in space, so the vorticity is not a measure, it's actual function. And moreover, U is exactly the same as U1 on 0t on 3. U is exactly the same as U2 on 2t on 3 to t. And in the meantime, between t on 3 and 2t on 3, the solution is almost everywhere smooth. So, and there exists a singular set of times, is non-empty, by the way, whose Hausdorff dimension is strictly less than 1, such that U is smooth on the complement of the set. C infinity of the complement across the torus. Okay, so that's the theorem in full glory. And it has several immediate consequences. So, in particular, it proves non-uniqueness because what you can do is you can take any smooth solution of Navier-Stokes you want for any data to be U1, and then you can take U2 to be a shear flow, which is also an exact solution, but with a different data. And in particular, you can set it up such that the kinetic energy of your shear flow at time capital T is larger than the kinetic energy of U0 at time 0. And if you have a weak solution which starts with some kinetic energy and ends up with a kinetic energy larger, that of course is not the same as the Leray solution with the same initial data, right? So you trivially have non-uniqueness. And you can prove non-uniqueness from smooth data, right? Because I said given any two strong solutions. You can also prove non-uniqueness from any L2 data, because all you have to do is take a Leray solution, wait a little bit of time, it's smooth, apply this theorem. Okay? So this really gives you non-uniqueness for any data, at least in this sense, for continuous in time weak solutions. Okay. So I guess the idea of the talk would be to give you a sketch of this proof. And this proof is based on previous joint work, which I had with Tristan Bachmaster, where we proved a similar result for 3D Navier-Stokes, but we did not have this information that the solutions were smooth on the complement of a thin set. And in fact, the method, as you will see, you can basically use it to solve a PD on the complement of a fractal, basically. It's very robust, at least a weak solution. No. Okay, so the idea of the proof is a two-step procedure. The general scheme falls under the umbrella of convex integration as developed in hydrodynamics by Delelis and Sekelichidi. They wrote a number of extremely influential papers on this topic in which they formalized the rather enigmatic constructions of Scheffer and Schneermann, and they put it in this very robust and beautiful framework related to the isometric embedding problem. So I guess I should say that's the convex integration step. So inspired by Delelis and Sekelichidi. But not exactly, in the sense that we have to do a different kind of convex integration, which is so-called, we call it intermittent convex integration. So it's not exactly this. As developed by Tristan and myself. And the first step, prior to the convex integration step, is a so-called gluing step. Which you should think of as a preparatory step to the convex integration step. And this is inspired by recent work by Philip Isett, who solved the Onsager conjecture for the 3D Euler equations. So Philip proved that given any Herder exponent less than a third, you can find the weak solution of 3D Euler, which is compact support in time and has that regularity. Together with Camilo and Laszlo and Tristan, we further improved a little bit Phil's theorem, showing that you can achieve any energy profile. And the gluing step, which I will use, is in the spirit of our work with Camilo and Laszlo and Tristan. So let me just say, Isett. He really came up with this beautiful idea of doing a gluing step prior to the convex integration step. So let me describe a little bit what these two steps are. So by the way, somehow this name convex integration stuck, the word convex, there's absolutely nothing convex here. So the old way of doing convex integration, more like Gromov kind, was convex because you were looking at the convex hull of certain configurations. There is no convex hull here and there's nothing convex. But somehow the name stuck. So the procedure, you relax the Navier-Stokes equations. So you write Navier-Stokes equations equals error, and you have an inductive procedure whose goal is to remove this error in the limit. So let's call these relaxed Navier-Stokes. So for Q, a natural number, you will find solutions of this equation . So this is the new thing, divergence of a traceless symmetric 3×3 matrix. And of course, VQ should be incompressible. So this is the equation you actually solve. The pressure is always taken to be zero mean, so I don't have to say anything about it. And you have two parameters. One parameter, delta Q, which is a sequence of parameters which go to zero. They will measure size of objects, in particular the size of the stress. And you have a sequence of parameter lambda Q, which measure Fourier frequency of objects, and they go to infinity. In fact, they go to infinity extremely fast. at a super exponential rate. So lambda q plus 1 is lambda q to a very, very, very large power of lambda q. And this one, delta q, is related to lambda q. It's an inverse power. This beta and that beta from the theorem are related to each other. Okay, so you have these two parameters, one sequence which goes to 0 extremely fast, one sequence which goes to infinity extremely fast. So what you require about the solution of this approximate relaxed Navier-Stokes system is basically two inequalities. Well, three, let's just say. First of all, that the stress in L1, so if you have L2 vector fields V, you see that this Reynolds stress R scales quadratically with the velocity. So if I'm going to have L2 functions here, I better have L1 functions there. So I'm not going to write L infinity in time anywhere throughout the stock. All my norms are L infinity in time. So this should be very small. And I will put a decoration here whose reason will become apparent later. So it's a bit smaller than delta q plus 1. And moreover, you require that VQ in L2 is uniformly bounded. So let's say it's less than a constant minus delta q to the 1/2. And moreover, you require that at the qth step in your procedure, these objects have Fourier transforms which are roughly localized at frequency lambda q. In a Gaussian sense, of course. So RQ and VQ live at frequency approximately lambda q in a Gaussian sense. So this is a lot of information now, because if I have basically essential support in Fourier and I have estimates on the L1 and the L2 norm, I basically know all the norms. And then by interpolation, really you know everything. Okay. So these are the assumptions, but the way I've stated these assumptions, there's nothing about partial regularity. So with these size and frequency assumptions, I will also construct a sequence of good sets and bad sets. So this is still part of the inductive assumptions. So there exists a sequence of good sets which are monotone increasing, they're nested. So the first good set is this one. And you have a monotone sequence, which keeps on increasing. Bad sets are their complement. Yep.
You said the frequency is around lambda q.
Yep.
Do you mean up to lambda q, or are you removing this small frequencies too?
No. So imagine they're supported in a ball of radius. So it's not in an annulus. It's in a ball. Bad sets are their complements. And I need to tell you, in order to get any hope for Hausdorff dimension less than 1, how the bad sets shrink. And the measure of the bad set at level q plus 1 divided by the Lebesgue measure of the set BQ is very small. And this is why I put this decoration here, because it's going to be small like this. And now you can immediately see why the Hausdorff dimension will be less than 1. So in the end, sigma t will be the intersection of all the good sets, of all the bad sets. Sorry. Sigma t will be the intersection of all the bad sets. So because this grows super exponentially, this will give you a dimension less than 1. But in addition, I know that the stress is 0 on the good sets. And moreover, once I have a good solution, an exact solution, once you have RQ is equal to 0, you have an exact solution of Navier-Stokes. Once I have an exact solution, I never correct it again. So that is to say that if T belongs to a previous generation good set, then the velocities are the same. That is to say, again, simply, once you have an exact solution, don't touch it again, ever. Okay? So these are the inductive assumptions, and of course, this is the new part with respect to my previous work with Tristan. Okay, so now let me describe a little bit this two-step procedure. So how will maybe I'll just use these. So let's say I have one of the intervals in the bad set. Okay, so what do? Maybe I should draw it bigger so that you can see. Is I subdivide this interval into many other intervals of with some parameter, theta q plus 1. Theta q plus 1 is related to the row coexistence time of Navier-Stokes with data vq. And again, if I know the L2 norm and I know the frequency localization, I basically know the local existence time. Okay? So let's say the only thing that's important, so it really doesn't matter. 1 over the H3 norm will do. Of course, that's not sharp. We wrote it just so that we don't have a lot of fractions. Okay? So, by the way, nothing is here is sharp. Everything is up to an epsilon. All right. Then, what you do is you call this interval t0, t1, blah, 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 ti plus 1. And you solve exactly Navier-Stokes. It's solution of 3D Navier-Stokes with initial datum vq at ti at time ti. So starting with ti, you solve Navier-Stokes with the initial data given by your approximate solution. Okay? So on any one of these intervals, you have a smooth solutions, right? So if I were to draw their kinetic energy, they would maybe do something like this. Now, of course, there's a direction of time in Navier-Stokes as opposed to Euler. In Euler, what you would do is you solve backwards and forwards in time, and you just glue around here. Okay? So in Navier-Stokes, what you have to do is you have to wait a little bit of time before you glue. You take this solution vi, you take vi plus 1, and then you have a partition of unity. And so on. And you glue them here. So the initial data at ti and the one at ti plus 1 are glued at the next time, so that this solution and this solution had enough time to regularize, to become super smooth. Okay? So these cutoffs, which I drew there roughly, of course have support proportional to theta q plus 1. But they are kind of sharp. The support of their gradient is much smaller. It's another parameter, tau q plus 1. And of course, you exactly know what I will tell you. It's by this much smaller than theta q plus 1. Because after you glue two solutions, the resulting error will only live on the support of the gradients of the cutoffs. So the set bq plus 1, the bad set at let q plus 1, will be the union of all these intervals of size tau q plus 1. And of course, the fact that this fraction is that is exactly the same what this fraction is this. Okay? So by gluing, I really mean the silly kind, where these cutoffs, let's call this chi I, form a partition of unity, and then you call vq bar the sum over I, some cutoffs in time, vi of xt. Okay? So it's really the silly kind of gluing. Now, because you glued, you have a stress, which is new. It's not the old stress, so you have an easily computable formula. So the new stress is a sum over I. It's essentially this. You get an error when the time derivative hits the cutoff. And then you have inverse divergence of Vi minus Vi minus 1 plus cutoff times 1 minus cutoff Vi minus Vi minus 1 tensor itself, the traceless part. So this inverse divergence, it's an elliptic operator which gives you for any incompressible vector field of zero mean, traceless 3×3 matrix whose divergence is your vector field, row by row. Okay? So now you notice one thing: to estimate the size of this error in L1, which is what you need to do, in the gluing step, you only want to achieve one thing. You don't want to decrease the size of the stress. It should be as big as it were. Just decrease, shrink it to a smaller set. So my goal is just to get this same estimate. Maybe I lose on this epsilon, but that's all. So the worst kind of term is actually this one, which gives you the time derivative of this very sharp cutoff. So now you need to estimate the inverse divergence of two solutions of Navier-Stokes, and this is a stability estimate in H-1 for 3D Navier-Stokes, which you can just do. And believe me, the estimate you will get is, so you have d by dt of the H-1 norm equals something. What should it equal? Well, if you have H-1 norm, it's going to be something proportional to RQ itself. It's a zero-order Calderon-Zermot operator acting on RQ. So the error should have size, this in L1, integrated in time, right? Because you pick up the time integral. But the time integral, you pick up this long interval, not the short one. So, and then the L1 size. And because of my definitions, this is exactly, so success, okay? You can also estimate this. This is an L2 stability estimate for solutions of Navier-Stokes. It's much simpler. Okay, so at the end of this step, oh, and by the way, you can make sure that this is also tiny. How tiny it should be? Well, proportional to the stress itself, square root. So this should be size square root. So basically, this is your estimate. And again, this is an L2 stability estimate. You can just do it. So this gluing procedure is kind of direct. Once you figure out what these are, you just pull it off. It's not that intense. So let me discuss a little bit the convex integration step. How much time do I have?
20 more minutes maximum.
Okay.
Good question. So the support of BQ plus 1.
BQ plus 1 is a set.
Yes.
Yes.
But it's a piece. It's composed of pieces, right?
It's many, many intervals.
Yeah. So BQ. How do we prepare?
So BQ is composed of many intervals of this size, right? We've zoomed in. And BQ plus 1 will consist of many intervals of the next size. And when I estimated their quotient, I took into account that there are many BQs and there are many open intervals in BQ plus 1. So they're just disjoint intervals whose length you know, and they're disjoint. So it's just a set. I mean, you should really think of the construction of the Cantor set. You have a big interval, you remove some pieces, you're left with some pieces. In the next step, you remove some intervals from there, you get some pieces. You're going to get a very thin Cantor set in the end. And that's just the construction. And in fact, if you want, you can think of the kinetic energy of the resulting function really as a Cantor-Lebesgue function, at least a decreasing version of it.
The similar set that you construct is independent U1 and U2.
No. You have, absolutely. You have a lot of freedom in making it. It's kind of fake. Okay, so the interesting thing is this convex integration step. And I hope to convince you of two facts in this convex integration step. One, your building blocks need to have three-dimensional intermittency. I will make precise what I mean by this. And two, it is important that time is there. This construction does not work if you don't have time. For stationary 3D Navier-Stokes, I have no idea what to do, and it's very hard. There is a student in University of Illinois at Chicago who proved it in 4D. It's a very nice paper, a student of Alexei Cheskidov. But in 3D, it's open. Okay. So I need to convince you of these two things. So let me write down the new velocity field as my glued velocity field plus a perturbation. And everything goes into the design of this perturbation. And the design is such that your inductive assumptions, which are on this board, are satisfied. And I've already convinced you that these inductive assumptions about the good sets are good. So all I will do now is two things: not mess up what I've done there. So once I am on a good interval, I will not touch the solution again. And two, I want to decrease the size. Okay, so let me write down what this is equal. So you write down the relaxed Navier-Stokes equation at level q plus 1, the one at level q, and you subtract them. So you get an equation. The divergence of rq plus 1 is equal to the divergence of wq plus 1 tensor wq plus 1 plus dt wq plus 1. I've written here, I forgot an important term. I've written here the important pieces that go into the construction, and next I will write down all my error terms. So there is such an error term, there are such error terms. And there's some pressure floating around everywhere, so. Oh, that's taken. Okay. Pressure is always the unique zero mean pressure you can get from that. We don't even discuss it. Okay, so what do I need to do? I need to make sure that rq plus 1 in L1, I need that this is less than lambda q plus 1 to the minus epsilon delta q plus 2. And the other thing that I need is that the perturbation has size which is square root of this stress. So this perturbation, I need to ensure it has, roughly speaking, this size. If I don't get this size, if I'm too small, I will never be able to cancel this stress. And if I'm too large, I will also not be able to cancel it. You really need to be of order square root. So this has to go in the design. So how can you possibly cancel this? Well, the perturbation wq plus 1 lives at a much bigger frequency, and now it's really in an annular sense. Approximately equal to lambda q plus 1, which is much larger than lambda q. So when you stare at these terms, the only possible way in which you can cancel this stress, which is a function of the very slow variable, is if this function of the fast variable with itself cancels. And it gives you low variable contributions which cancel this. So the only possible way is, again, let's say the high, high, low interactions. So I have two high frequencies spit out a low frequency. The only possible cancellation can come from a high, high, low interaction. Otherwise, everything else is error. Okay? So there's a very simple linear algebra lemma you can write down, which states that given any matrix in the ball of radius 1/2 around the identity, you can span it, any symmetric matrix, you can span it with simple vectors. So there exists a set capital lambda of 6 elements on the sphere, such that, and there exist smooth functions defined on the closed ball of radius 1/2 around the identity into R, C infinity smooth, such that this identity holds for all r in the radius, in the ball of radius 1/2 around the identity. Symmetric. Symmetric matrices. Again, you have a symmetric matrix. It's positive in a certain sense, and you can write down positive matrices there. Okay, so this is linear algebra, and with this linear algebra in hand, you can kind of see how this high-low interaction will work. You will design the perturbation as follows. This is a sum over xi in the set lambda of these smooth functions. Well, what you actually do is this. Times some very highly oscillatory function in space and time. I will tell you much later what this is. But you can already see that if I ensure that wxc times wxc prime is identically 0 for all xc not equal to xc prime, and if I ensure that the mean on the torus of these vectors with itself is xi tensor xi. So if I manage to ensure this, then of course when you tensor this with itself, the low frequency contribution only comes when you average the fast variables. You get xi tensor xi. You square these things, so you get gamma squared of this object. And the reason that you write this object is that this object is in the neighborhood, is in the 1/2 ball around the identity. And these 1/2 becomes 1, which exactly will cancel this, okay? So you have basically added a pressure by doing this. Okay, so this is how my perturbation will look like. And now what I need to tell you is how these highly oscillatory functions look like. And that's the principal part. First of all, what should be their size? We know what frequency they should live at. What should be their size? And this is, I guess, not emphasized enough. This, let's call this function somehow so that I don't keep on writing this. Let's write it as a sub xi of rq. And again, if you think of it as root rq, you would be correct in terms of every single estimate. This is a function of slow variables. This is a function of fast variables. So when you multiply them and you compute norms, they decouple, right? So you have a decoupling lemma which basically goes like this. Without this decoupling lemma, nothing works, okay? And this is very easy to prove. As soon as this is a periodic function whose period is larger than the frequency of this object. So what I will ensure is that wxc will be periodic. So this works if wxc is periodic with period much larger than 1 over lambda q. Okay, because that's the frequency of this. That means it has enough time to average itself. Okay, so this the correlation lemma, once you have it, you now try to compute the L2 norm of the perturbation. And again, you have to ensure that this is true. So you compute, and you have decoupling. And you have root RQ in L2, that's exactly RQ in L1 to the 1/2. RQ in RQ bar, sorry, because it's the glued object, which already has the correct size. Where was it on the previous board? Here. So square root of that, this object already has size delta q plus 1 to the 1/2 again. So the only possible thing you can do here is make this of size 1. Because otherwise, the product, you will get destroyed. Okay? So another constraint on your highly oscillatory building block, its L2 norm has to be size 1. Okay, so now let me discuss what you do with the Laplacian. So the Laplacian is an error, but to put it in RQ plus 1, you need to invert the divergence. An inverse divergence of the Laplacian is basically the gradient. So you have to estimate the gradient of WQ plus 1. But importantly, WQ plus 1 is a velocity, so it's an L2 object. But that object is a stress, so it's an L1 object. So you need to estimate this in L1. Okay, the gradient essentially, worst case, it hits the fast variable. So it's going to cost you lambda q plus 1 because it's the fast variable. And then you again have L1 decoupling. So you have AXC L1, WXC L1. And this I knew that it has L2 norm of size 1. So what I'm going to do is I'm going to say it's lambda q plus 1. This I cannot really use. It's not good enough. But let me write down anyway what it gives you. It gives you this. But you can ignore it. And here you get the measure of the support to the power 1/2 times the L2 norm. But the L2 norm is size 1, right? So I'm 1. Okay. So three-dimensional intermittency enters. How in the world are you going to make sure that this is less than this? This is not going to help you. This size of the support to the 1/2 better beat the crap out of this lambda q plus 1. So the size of the support of WXC has to be much, much less than lambda q plus 1 to the power -2, right? Because it's square root and power 1. So if your building blocks are two-dimensionally small, think of tubes, they will be useless for this construction. They will be very useful for other constructions, such as Euler, but they will not help you here. You really need three-dimensionally small objects. Objects whose support is more like balls rather than tubes. Okay, so how are you going to design this? And there is a fundamental difficulty with this, basically. The fundamental difficulty is that we are not able to find any building block which is three-dimensionally small, and it's approximately a stationary solution of 3D Euler. Tristan and I tried for a very, very, very long time, and we failed to do that. So ideally, you would like that this is a pressure gradient plus a small error, and we are not able to do this. Okay, but remember, time is here. And time is here to help us. So let me now actually describe the building block and tell you why time helps you. So you make the periodic box and you periodize it at some frequency which is much larger than lambda q inverse. So it's more related to lambda q plus 1 inverse. So the frequency, the box size is lambda q plus 1 inverse, and there's another parameter, L perp inverse. I will tell you what L perp means. So let me now zoom in into a box. So if you look at any specific box, the previous construction of Szekely-Hidi and Daneri Szekely-Hidi, they constructed Mikado flows, which are basically straight tube flows. They are flows in which the velocity points in one direction only, and their support is, has cross-section orthogonal to this direction, and it's of finite width. Okay? These are the Mikado flows. And as I told you before, Mikado flows are tubes, so they are only two-dimensionally small. And you would like to make them three-dimensionally small. By the way, Mikado flows do obey this, but they're just not three-dimensionally small. So what we do instead is we take one of these tubes, right? It's periodized, right? So, and through this tube, we shoot fluid. Fluid is an elliptic parcel of fluid, and it moves in this direction, and then it comes back at some incredibly high speed in time. The size of the parcel here, cross size, is lambda q plus 1 inverse at zoomed in, right? And length is much, much bigger, and it's of size, well, more parameters. L perp inverse L parallel. So what does this parallel and perp mean? If you were to scale out the lambda q plus 1 and you would scale everything to the unit size, this ellipse has L perpendicular width and L parallel length. Why do these parameters matter? Because you should ask yourself, now that you've cut this Mikado flow, you have an elliptic fluid parcel, is it incompressible? The answer is of course not, it's not incompressible. But you can compute how big the incompressibility corrector should be. And the incompressibility corrector should be of size L perpendicular, L parallel inverse times the original size. So if this length is much bigger than this length, the incompressibility corrector is small. Okay? So the only reason why you cannot work with balls, actually, you need to work with very elongated ellipses, is that otherwise your flow is not approximately incompressible. Okay. So now let me tell you a little bit more about this shooting of the fluid. Okay. So you can compute this. I probably just need 2 more minutes. It's a pressure gradient, sure, and you have errors. And the errors are of this size. So xi, by the way, is this arrow. It's that arrow from there, okay? Xi dot grad this is what you get, plus small, due to incompressibility. This object is not small. It's very large, even if you write it as a divergence. However, if your building block looks like some bump function which has these dimensions, and in the regions orthogonal, so in this direction, it's just a function of x dot perp, but in this direction, you solve a transport equation, then you will be able to change xi dot grad by dt minus 1 over mu dt. Notice this kills the mean, projection on non-zero means of this. If you take this parameter mu to be incredibly fast, there is a barrier to how fast it can be. It's the parabolic length scale, lambda q plus 1 squared. You cannot beat that one. Then, what you do is you add one more corrector, which we call the temporal corrector. And I, of course, erase the equation. You can prove that this, of course, will cancel this now. And you will get other small terms, okay? So that's essentially the construction. You have to believe me that I can choose all these parameters, and of course this works. And in closing, I just want to say one thing. This method is what I call L2 critical. The Navier-Stokes equations are obviously not L2 critical. L2 is the only conservation law in the sense that it's not increasing, but scaling is not critical for L2. Of course, since the work of Lyon's, we know that if you put Laplace into the 5 quarters, that's L2 critical, and we know that the equations are globally well posed. The same method, as I've described here, works for all powers of the Laplacian strictly less than 5/4. So if you replace the Laplacian Navier-Stokes with any power less than 5/4, you will be able to prove the same theorem. And without this partial regularity, this was also noticed in a recent preprint by Luo and Titi, who also had this observation. And again, this method is really L2 critical. And that's what I will say in closing.
Thank you very much. Questions, comments?
So you said it's L2 critical, so presumably if you change L2 by some LP for P larger than 2, something has to collapse.
Yes.
What is it?
This cancellation is not an LP cancellation. You would really need to devise the way I cancel the stress is really pointwise, which is really an inner product. I have one object at high frequency, inner product with another object at high frequency gives you zero mean. That's an L2 construction, because it's the L2 inner product gives you zero mean. You need an LP version of that, where you have multilinear things, but P is less than 3, on the other hand, so it's non-trivial how to do that. But you need an LP cancellation procedure, not an L2-based procedure.
Thank you very much. Further questions or comments? There seem not to be too many questions or comments. Let me just add that this was, from my point of view, a remarkable presentation, stretching from Leray up to current result, full of activity, energy. Thank you very much for all the details.